From the beautiful plush studios of Way Happy, this is Mr. Meyer and 11-2 probability. Now, probability is a measure of how likely an event is to occur. Now, what's an event? An outcome. So you do something and you want to know you measure the outcome and you want to know what was the chance that would happen. That's called probability. Now, remember, probability is always between 0 and 1. You can see that in the bottom right-hand corner of the notes. It is impossible, 0% chance, or 0 happening. It is for certain going to happen, 100% chance, or a probability of 1. You can give probabilities as decimals, fractions, percents, doesn't matter. Just promise me you'll stay between 0 and 1 or 0 and 100%. Because that drives people absolutely crazy when you get a number that's bigger and you don't realize that that's not possible. So stay between 0 and 1 or 0 and 100%. There's all these different outcomes. Now there's a sample space. Sample space is what kind of things we would predict from our experiment. So if you roll a die, a regular old die, or what the books like to call a number cube, if you roll a number cube has 6 sides. There's 6 possible outcomes usually, right? The numbers 1, 2, 3, 4, 5, 6. If you have a spinner right next to it, 4 colors on the spinner, that the sample space, or what are the likely outcomes, would be blue, yellow, green, and red. So those are what are called a sample space. Those would be the outcomes you would expect. All right, equally likely outcomes are things that are, fair. They have an equal outcome. Rolling a number on a die is fair. There's not more than one number on there, and they're all equally represented. So that's called equally likely outcomes, or that spinner that you see there is equally likely because they are all a quarter of the circle. So therefore, they were all fair. All right, let's try example 1. You take the letters probable and you write it on a separate card. Each one gets a 3x5 card. I turn them all face down, I mix them up, and then tell you to pick one. What's the chances that you pick a constant, right? So not a vowel, right? So you pick one. What is the chances that you flip it over? Well, what is probability? Probability is this right here, theoretical probability. It's this favorable outcomes or the success you're looking for. Count how many ways. We just did that section on counting. Count how many ways you can achieve what you want. In this case, a consonant. If you can, how many ways can you get that? And you divide it by how many ways were there total, right? That's the probability. So the numerator should always be smaller. So the probability of selecting a consonant, right? So a lot of people will write this as probability of consonant. All right. What is that? Well, how many ways are there to pick one? Well, according to my calculations, there is 1, 2, 3, 4, 5. There's 5. There's 5 that are successful. You could either pick a P, an R, a B, or an L, and all of those would be winners for us in this game. So there's 5 ways to be successful or favorable outcomes. And how many total are there? Well, that thing had 8 letters. So you have a pretty darn good chance, right? You have a 5/8 chance of being correct. Now, you could give that to me and the answer is 5/8. You could give that to me as the decimal. You could give that to me as the percentage. Any of those will work, in our favor. And we would like any of those. So you can give me any of those 3 answers. I don't care which one. Unless it says use a fraction. 2 number cubes are rolled. What's the probability that the difference between the 2 numbers is 4? Ooh. So, I'd have to be like probability that the difference of 4. That's a little harder because first of all, I have to figure out, how many ways can you have a difference of 4? So what are you talking? You can't do 4 and 0. So it'd have to be, it'd have to be 5 and 1 or 6 and 2. Or what if you reverse that? What if the 2 came first? So 2 and 6 or 1 and 5. I think that's it, right? I think that's the only way you can have a difference of 4. So therefore, there's 4 favorable outcomes over. Now, how many outcomes are there when you roll 2 dice? Well, you have 6 outcomes, and then you have another 6 outcomes. So 6 and 6, that's 36 outcomes. Holy macaroni. So 36 outcomes. So 4 out of 36, that's the chance that the difference between the 2 will be a difference of 4. And that reduces down to what? Cut them both in half is what I tell my daughter. 2 out of 18. Oh, wait, cut them in half again. 1 out of 9. You have a 1 in 9 chance. I know that decimal is 0.11111 repeating forever, or an 11% chance, 11.1% chance of that happening. So next time you roll 2 dice, if the difference is 4, you should be like, whoa, what were the chances? Like 11%? And people would be like, I don't know, let me calculate. And they'd be like, wow, how'd you know? Well, I remember back in this day in Algebra 2. Go ahead and do a problem. We'll be right back. Beautiful work. All right, let's start talking about complements. Now, complements in probability are kind of like, think of them as the opposite, right? If there's a 20% chance you're going to win the game, then there's an 80% chance you're going to lose, right? Or I like to think of it when you look at your iPhone weather and you see that there's a 30% chance of rain, and people are like, wow, there's a 30% chance of rain. It's a 70% chance it doesn't rain, right? And so, kind of think of that as the complement. Sometimes it's easier to count the complement by subtracting it from 100% or 1. And that's all that is saying right there in the little box. Now, here's example 2. There are 25 students in the hall, in the student hall, and I walk in there and I ask them, hey, I see you guys are studying for a foreign language, and I count them up. I'm like, how many people are doing French? Wow, 6. How many are doing Spanish? 12. Japanese, 3 more. What is crazy? And then I'm walking out. I wonder how many people aren't studying a foreign language in the student hall. And so I know from that quick math that there was 21 people out of the 25 that were studying a foreign language. So if I wanted to figure out the percent that weren't, I would use a complement, right? So I would say that if you do 100% or 1 minus the 21/25 that were already studying, then I know that 4, well, get a common denominator for those of you not sure. I know that 4 out of 25 were not studying a foreign language. So that would be the complement to the people who are studying. Or if somebody just asked you who wasn't studying, you could use complements to figure out what percentage or what fraction of the people were not studying a foreign language. So that's a complement. Now you're kind of ready to go and just have fun. So look at my example 3. Each student gets a 5-digit locker combination. What's the probability of receiving a combination with all odd digits? All right. So I think I would have liked a little more info here. 5-digit locker combination. Thank you. So it has 5 digits. Well, again, what's the probability of all odd? Well, I have to do the probability of odd over the probability of the total. Like, how many are there? No, I'm sorry, not probability. The number. I shouldn't say probability. That's bad. I should say the number of ways that you can be odd, and over, some of us are very odd. The number of ways you can be odd over the number of ways to be these total combinations. So let's do our counting principles. How many ways are there to have odd? Well, it didn't say anything about repeating. What is our sample space? Our sample space is 0 all the way to 9. So there's 10 digits. But how many of those digits are odd? Well, let's see. There's 1, 3, 5, 7, 9, 5 of them. So 5 are odd. All right. So your first digit to be odd, there's 5 ways. And then your second digit to be odd, there's 5 ways. And your third digit to be odd, there's 5 ways and 5 ways and 5 ways. So there's that many ways I can count up to get odd, 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 odd. Divide that by how many ways can you make a combination? Well, there's no restrictions on combination, right? They could be apparently 0, 0, 0, 0, 0 all the way to 9, 9, 9, 9, 9. So there's a lot. So you're going to have 10 times 10 times 10 times 10 times 10. And now you can calculate that beautiful probability. Now you might notice some reducing would come in very handy here, like a half times a half times a half times a half times a half. That would be pretty nice to know. Maybe you wouldn't notice it, and maybe you would do all the math. So I'll do it all out. I know we'd probably grab our Sheilas and we go 5 to the 5th is 3,125. And let's see, this is a 1 with how many zeros? 1, 0, 2, 0, 3, 0, 4, 0, 5, 0. 1, 2, 3, 4, 5. All right, there's your answer. So you could take that and you could divide it by a 1 with 5 zeros. 1, 2, 3, 4, 5. And you get that much of a chance. I could even go math change to fraction. And what? It's 1 in 32? That's crazy. Oh, wait. A half times a half times a half. That's all it really was, right? A half times a half times a half. That was a half 5 times. So that'd be, yeah, 1 over 32. So fraction answer 0.03125, decimal answer, or a little over 3% chance that that would happen, that you would get all odds. Pretty crazy, right? All right. And what about this last one? The table shows the result of a spinner experiment. Find the experimental probability. So, experimental probability is when you actually do an experiment and you try to find the probability from your experiment rather than using theoretical, which makes sense. So, which you could calculate. Like, no one told me the spinner were all equal sizes or anything, or the same number was represented the same number of times. So, I don't know. We just did an experiment. So, you can see the spinning of 4, it happened 14 times. So again, you do the success, what I like to call the success, or the favorable outcomes over the total. So what is that? Well, the success of spinning a 4 was 14 over the total number of spins. Anybody know what that is? That looks like what, 20, 30, 40, 50 spins? So I think it's about 50 spins. So there's your experimental probability. I guess cut them in half, 7/25. There is your experimental probability. Or what about a number greater than 2? Well, again, success over total. So how many successes do we have that are greater than 2? We have a 19 outcomes for 3, and you have 14 outcomes for 4. You're still over 50 because you still have 50 different spins that you made, but now a number greater than 2 are those 2 outcomes. So what is that? That's like 33. So 33 50ths, or a 66% chance, much more favorable, that you will spin a number greater than 2. All right, let's ask you a question and we'll be right back. Nice work. Now, what about using a little geometry in your probability? Why not, right? Come on, mix two things you love together: geometry, probability. Oh, heaven. Look at that drawing right there. That drawing is just a shaded region. Who knows what it represents? A prize, and you're throwing a bean on there, and we're going to see if the bean lands in the shaded region. So really what I'm doing here, it says pick a point at random. What's the chance that the point's in the shaded region? Well, that's pretty hard to figure out unless you know a little thing called area, because look at the shaded region. I could find the area of the shaded region, which would be our success, and I could divide it by the area of the entire shape, which would be our total. So again, I'm going to go area of the shaded over the area, the total area of that shape, and that will be what we're looking for. So total area, kind of easy, right? It's a 9 by 9. 9 by 9. Hey, that's 81 centimeters squared, or squared centimeters. So 81 centimeters squared, done, right? Now, what about the top, the shaded region? Well, most of us will say, piece of cake, right? It's triangle 1/2 base times height. So you're like, all right. So it's the area of the triangle is 1/2 the base, which is 9, times the height, which is 9, which is 81 over 2. Ugh, that doesn't go in nicely. But not the whole thing. That whole triangle isn't shaded, right? There's this little 4 by 3 out there. The area of that little rectangle is 4 by 3. That's not shaded. So there's a little 12 units, 12 cubic centimeters, square centimeters, that aren't shaded. So we got this 81, and then I got to take 12 out of that, right? So what is that? I'm going to do 81 halves minus 12, which is 81 halves minus 24 halves, which, I don't know, anybody help me there? Is that 55 halves? 55 halves. I think that's what it is. I think that'd be 79. I don't think it's 55, because if you add that together, you get 79, not 81. Yeah. So you might want to change that. That's not really that. It's 57, I believe. Oh, dang it. 57. Oh, look how quickly I fixed that. 57 halves. That is the shaded region. So your shaded region is 57 over 2 centimeters squared. So what is our chance of success? Well, whatever the heck 57 over 2 divided by 81 is. So how funny that my daughter just did this today. 57 over 2 divided by 81. I told her, hey, do copy dot flip. You copy the first one, you change it to dot, and you flip the second one, and that's going to be your answer. So what is that? 57, like Heinz 57 over, what is that, 162? 162, 6, 7, 8, 9. Hey, they're both divisible by 3. Now, how do I know that? Add the digits up. 5 plus 7 is 12, and 12 is divisible by 3. So that means 57 is divisible by 3. It's 19, right? And what about 162? Oh, well, this sounds a little harder. 6, 7, 8, 9. So they add up to 9. 9 is divisible by 3. That means 162 is divisible by 3. So is that 54, I think? 54. Now, those aren't divisible by 9. The 3, the bottom one is, but the top isn't. In fact, 19 is prime. So I'm done. There is your probability of success. Now, you might want a percentage because people like percentages. Grab a calculator, right? It's, around 35% or something like that, or, who knows, somewhere around there. And you can see. All right. Have a great day. Stay happy. See you tomorrow.